Hey everyone, it's Dr. Calkins again. We're going to wrap up our week 4, chapter 16 lecture by talking about reactions. Remember, an unstable nucleus needs to fall apart to be more stable, whether by changing protons to neutrons or the reverse, or sometimes just losing a large chunk. We'll talk about all of those. First one we're going to talk about is beta. Remember, beta is an electron. So when we do beta decay, what we're looking for is a neutron to become a proton. So we have a neutron and it becomes a proton. So as we look at an example, one of the best examples for this is carbon 14. So carbon 14 is 14 in mass carbon, and carbon is number 6 on the periodic table. So periodic table, definitely your friend on this because it'll tell you who's going to go forwards and backwards. And what's most important about beta is it goes forward. One box. So that helps us with the homework, especially if we don't like math. So if we look at carbon 14 in the periodic table, or at least carbon in the periodic table, we notice that forward is nitrogen. So as we move forward to nitrogen 14, that's number 7. So notice our 0 became 1, our mass stayed the same, we gained 1. But in order for that to happen, we need to release a 0, -1 electron. We call that a beta particle, so that would be beta emission. So let's think about what happened. Nuclear chem is nice in the sense that the math is relatively easy because 14 equals 14 plus 0. So notice this number needs to be these numbers, added up. Just like this number needs to be these numbers, added up. Just remember 7 plus a -1 is the same thing as 7 minus 1, and that's 6. So what happened here? Well, again, we have a neutron, but somehow it became a proton. So a good cartoon way to think about this is maybe what a neutron is. So if a neutron is a 1/0n, maybe that really is a proton and a electron together. If this is an unstable nucleus, it's so angry that it's just saying, the proton's basically evicting the electron, and it's our particle. And what happens in the end is our mass stayed the same, but because we got rid of our negative and our positive made our neutral in the first place, now we get an electron from inside the nucleus, which is kind of crazy to think about. We've never talked about electrons in the nucleus, but that's exactly what's happening here. So if this is what represents a neutron in real life, and it probably doesn't, but it's a good cartoon theme of how it could work, we have 1 and 0 make 1, 1 and -1 make 0, and we're just allowing the negative to leave so that positive remains and 6 can become 7. And that's beta decay. It's the only way to move forward in the periodic table towards that band of stability. So let's try another one. Another one that's pretty common is positron emission. So positron emission is a lot like what it sounds. We're using the 0 +1 electron instead of the 0 -1 electron. So this is the positron itself, and this is a way to move back one box in the periodic table. So because we're going back one box, that means we're going to take our proton and turn it into a neutron. That's the only way we can go backwards. A good example of this is potassium 40. So K40. Potassium on the periodic table is number 19. And it can go backwards. And if we look at the periodic table, we're here. Potassium 19, we're going to have to go back to the previous row. That's going to be argon 18. So we're going to go back to argon 18, but notice the mass stays the same. 40 equals 40 still. 19 equals 18, never. But that's because we have a particle missing. That's a 0, +1. This is called positron emission. Emission's like your car. it leaves the reaction. So our positron is leaving our nucleus. So let's think of a cartoon way of how this works. Let's imagine that we have our proton, which is 1 over 1 p. So what that means is we have a massive one and a positive charge of 1. So really, if it's just this, we're saying positive charge, goodbye. It's a proton losing its positive. And that's exactly what a positron is. So if we take this away, make it a 0, that's exactly what we want, and that's a neutron of the same mass. So we stay the same, we just go backwards a box in the periodic table. Maybe that's what it needs, and in this case is for potassium-40, that's what it needs to become non-radioactive. Whereas carbon-14 was used to age dinosaurs, because when you stop eating carbon, your carbon-14 disappears, but your carbon-12 doesn't. So if you're frozen in a glacier, like a woolly mammoth, that's the case where you can backtrack through half-life, how long it's been there. But potassium-40 does this, and potassium-40 is found in, say, bananas. So even bananas are radioactive to a small extent because of the potassium-40. You'll see a lot of potassium-40 in our good bed, the nuclear kind of lab. Most of our samples are using potassium-40, especially granite. Granite rock also produces these positrons, so it is radioactive to go to Elephant Rocks or Johnston shut-ins. It's also radioactive to have a granite countertop in your home. So much so that you get a little bit of radiation from it, and food can last longer on the countertop because it's getting showered with radiation every second of every day. So your bread might last a few days longer, or your fruit can stop from molding a few days quicker, all because of that. And that's positron emission again. The key here is you can go backwards one box. Let's try another one. So the next one is really accomplishing the same idea. It's electron capture. So electron capture is when a 0, -1e is brought in instead of kicked out. This too is a way to go back one box, just like positron emission. So what happens here is a proton still becomes a neutron, just in a different way. A good example for this is mercury. Mercury, specifically 197, is number 80 on the periodic table. You can add an electron to it and now do the math. Remember, the arrow is still the equal sign. So 197 still equals 197. That's the easy part for all of these. But now we have 80 subtract 1, that's 79, and now this is gold. If we look at the periodic table, mercury just moved backwards. One box, just like we'd expect. So if you don't like the math, just think of the direction. So how did this happen? Well, again, if a proton is just a particle, it's 1 over 1p. We have 1 over 1p inside. We're saying, what if an electron gets sucked in? If it gets sucked in, now we have a 0, -1 electron, and now that's really just a neutron. Because 1 and 0 make 1, 1 minus 1 makes 0, and that's really just the reverse, the exact reverse of beta decay. So what's most important about this is both electron capture and positron emission go backwards, one box. It's just two ways of doing the exact same thing in different ways. The only disadvantage of electron capture is you're capturing electrons from an outside source. So this is not a form of radiation that can be useful in hospitals because you're pulling in particles, you're not ejecting them out so that other machines can read them. Let's try the last two. Next one is alpha. Alpha is important only because the big ones do this. So alpha decay, the biggest, heaviest particle, the least dangerous in the sense of damage. It does do damage when it hits, but again, it's not moving very fast because it's so large in mass. So think of a tank versus a sports car. This is the tank. It goes slow, but when it runs you over, it hurts. So can a sports car that's going really fast. Alpha decay is 4 over 2 helium. That's the particle size. Again, it looks like a swimming fish instead of a diving fish in the Greek alphabet. A good example for this, and typically you have to be above 83 on the periodic table. So if you find 83 on the periodic table, that's bismuth. So it's really after bismuth, so anything from 83 to 118, usually capable of doing this because most of those are radioactive. An easy way to see radioactivity on the periodic table is look at the weights. The weights that have brackets or parentheses, those are radioactive elements. And that tends to be after 83 for most. So here, a good example is uranium. So uranium-238, it's number 92 on the periodic table. Uranium can lose an alpha particle and become 234. Helium is the size of 2 protons, so you're going to lose 2. Because when you kick out, and this is thorium on the periodic table for number 90, you get 4/2 helium, and that's a alpha emission. So what's important about this one is notice the number changed. This is the only time the number changes because 234 and 4 make 238. We're losing something of size. It's kind of like uranium is so radioactive it has leprosy and it's falling apart. It's losing its, ear, its elbow, that kind of thing. It's kind of like the doctor went to uranium and said, you're going to die unless you lose 20 pounds in 5 seconds. How do you do that? Well, you pull out a knife and chop off a chunk. Chop off an arm. So that's exactly what alpha is doing. It's taking something that's way too big to survive, chopping off in this case, our largest chunk possible, which happens to be the size of helium, and that'll move it back 2 boxes. So what's nice also about this one is you're going to go back 2 boxes in the periodic table, and that's the only one that does that. So we could expect that if we look at uranium, it's going to go back 2 boxes to thorium. Oftentimes with alpha, gamma is also produced. So gamma rays, that's 0/0 diving fish. So again, it's swimming fish versus diving fish in the sense of the Greek alphabet there. But if somebody chops off your arm, you're going to scream, and that scream is a gamma ray. So oftentimes alpha and gamma rays are produced at the same time. But if we were to do the math on just a gamma ray, we could use uranium one more time, and we would still get uranium afterwards because it's 0/0. So it stays exactly the same in gamma, but again, if gamma is produced with alpha, you'll still do that subtraction of 4 on top, 2 on bottom. But again, gamma ray is energy, so when you hack off a chunk of uranium, gamma rays are often produced. That's the kind of subatomic scream that we get from those subatomic particles getting lost from that nucleus. There's 2 other reactions that are useful, but before we get to those, I want to briefly mention what we just covered in detail. So this cute way in our notes in our lab is probably the best way to show it. You can go either forwards or backwards. So if you go to the right, beta, exactly what we said, mass stays the same, atomic number increases by 1. If you go backwards, there's 2 ways, positron or electron capture. And again, that's just dependent on who's who. You're never going to see both of those in the question at the same time because there's no way to know unless you see the entire reaction. And then alpha can go backwards all the way. And this is the most important chart of this particular homework. So if we look at that kind of real life example that we just did, if you don't like the math and adding and subtracting negative numbers, just remember that if you move forward, that's beta. If you move backwards 2, that's alpha. If you move backwards only 1, that can be positron or electron capture. So there's 2 ways to go backwards 1. There's only 1 way to go backwards 2, and there's only 1 way to go forward. So if you don't like the math, remember the directions, and you're in better shape. So 2 real quick ones that are mentioned briefly, and then this one's finished. We have fusion. Fusion is basically taking 2 atoms into 1, so the sun can do this. This is the power of the sun and the stars. So you can take a hydrogen and another hydrogen, and you can make a helium. If this was a 2, this was a 2, this would just be a 4. So that's fusion. You're basically just welding these two atoms together to make a larger one. And